A new aircraft is promising to make travel possible direct from Sydney to the United States and the UK, making Australia even more accessible to the world.
The Airbus A350 is among the industry's most modern twin-engined wide-body airliners.
Ever wondered how tough modern airliners really are? It's not just smooth flying. These planes endure extreme tests, from being frozen in a giant fridge to withstand icy altitudes, to having chickens shot at their cockpit to simulate bird strikes. Let's dive into the fascinating world of what it takes to ensure your safety in the skies. Over the past decade, the way we test modern airliners has evolved dramatically. The shift from traditional flight tests to advanced ground-based evaluations and computer simulations is more than just a technological leap. It's a crucial step towards enhancing safety while reducing the time and cost of testing planes in the air. The goal: to catch potential issues before an aircraft even leaves the ground. The push for these rigorous tests has been driven by the lessons learned from past tragedies. For instance, in 1985, a commercial airliner crashed during a thunderstorm in Dallas-Fort Worth, a disaster that highlighted the need for better storm-related safety measures. Then, in 1996, a TWA flight near New York fell from the sky due to an electrical fault. These accidents were wake-up calls for the aviation industry. One of the leaders in this push for innovation is Airbus, a company that has become synonymous with cutting-edge aircraft design. Founded in 1970, Airbus has grown into one of the world's top aircraft manufacturers, producing everything from military jets to some of the most iconic commercial planes, including the A320 family and the massive A380, the largest passenger plane on the planet. In 2015, Airbus introduced the A350 XWB, a family of long-range, wide-body airliners. What sets the A350 XWB apart is its construction. Its fuselage and wings are made primarily of carbon fiber-reinforced polymer. Before any new Airbus model can take to the skies, it must undergo static ground testing, one of the most critical phases in aircraft development. This process includes mechanical load tests and pressurization evaluations designed to push the plane to its absolute limits. During these tests, the aircraft is outfitted with sensors and strain gauges that measure how different components respond under extreme conditions. One particularly dramatic test involves bending the plane's wings to almost 90 degrees, far beyond what they would experience on a normal flight, to ensure they can handle even the most severe turbulence. In December 2013, Airbus performed the ultimate load test on a specially built A350 XWB, subjecting its wings to forces 1.5 times greater than anything they would encounter in service. The results were astonishing. The wingtips deflected more than 5 meters, a clear indication of the plane's extraordinary structural integrity. The final stage of testing involves pushing the wings to the breaking point, literally. By doing so, engineers can determine the exact load level at which the wings will fail, ensuring that this threshold is well beyond anything the aircraft would encounter in real-world conditions. Pressurization tests also play a crucial role, subjecting the aircraft to air pressure similar to what it would experience during various phases of flight. These tests help identify any potential leaks and confirm that all seals and joints maintain airtight integrity, further ensuring the safety of passengers. Extreme weather testing. Now, the A350 also marked a significant milestone for Airbus, being the first to face a new level of extreme weather testing. At the US Air Force's McKinley Climatic Laboratory in Florida, the A350 XWB was subjected to temperatures ranging from a blistering 45 degrees C to a bone-chilling -40 degrees centigrade. This testing wasn't just a routine check. It was crucial for ensuring that the aircraft systems could perform flawlessly under the harshest conditions. But Airbus didn't stop there. The next challenge was even more intense. The A350 XWB was sent to Iqaluit, Canada. Unlike the controlled environment of the McKinley laboratory, these tests put the A350 to the test in actual freezing conditions. Everything was under scrutiny. The aircraft itself, the flight crew, the ground crew, and even the refueling equipment. The goal? To make sure the A350 could handle whatever Mother Nature throws its way. Even with these rigorous tests, the fight against extreme weather doesn't end there. Icing is a constant threat that can drastically affect an aircraft's performance. Ice buildup on critical areas like wings and control surfaces can disrupt lift, increase drag, and jeopardize the plane's ability to take off, maneuver, and land safely. That's why deicing is a mandatory procedure, even for the toughest planes. Deicing usually happens right before departure. Ground crews use a heated mixture of propylene glycol or ethylene glycol and water to remove any ice, snow, or frost. They also apply a second fluid to prevent new ice from forming during the flight. Once the deicing process is complete, the plane is carefully inspected to ensure it's ready for takeoff, free from any lingering ice that could pose a risk. Runway maintenance. When it comes to ensuring flight safety in cold weather, it's not just about keeping planes in top condition. The real battle often takes place on the ground. Airports worldwide face the daunting task of keeping runways, tarmacs, and other infrastructure clear of snow and ice to prevent travel delays and accidents. This is where specialized snowplows and brushes come into play, tirelessly working to clear runways and taxi areas of accumulated snow. But snow removal is only part of the equation. Deicing chemicals like potassium acetate and calcium magnesium acetate are critical for preventing ice buildup and ensuring that these surfaces remain safe for aircraft operations, even in the harshest conditions. Some airports take it a step further by installing advanced heating systems beneath the runway surfaces. These systems are activated during snowfall to melt snow and prevent ice from forming in the first place. Meanwhile, dedicated teams of airport personnel constantly monitor weather conditions and runway surfaces, performing regular friction tests to assess the level of grip available for aircraft during takeoff and landing. It's a complex and continuous effort to ensure that every flight can proceed without incident, no matter how cold it gets outside. But while commercial airports have the luxury of delaying flights during extreme weather, the stakes are much higher for military operations. Military aircraft must be ready to deploy at a moment's notice, regardless of the weather. This is why the United States and other military powers invest heavily in rigorous testing to ensure their aircraft can handle any situation. One of the key facilities in this effort is the propulsion wind tunnel at Arnold Air Force Base in Tennessee. This site is home to two full-sized wind tunnels, one for supersonic flight and another for transonic flight, plus a smaller tunnel focused on transonic aerodynamics. These tunnels simulate a wide range of flight conditions, playing a crucial role in the design, development, and improvement of military aircraft and aerospace systems. The facility is capable of simulating speeds up to Mach 4.75 or over 3,600 miles per hour. In addition to wind tunnel testing, the U.S. Air Force uses the McKinley Climate Testing Laboratory's climatic chamber to evaluate its aircraft. One notable example is the F-35 Lightning II, the most advanced and expensive fighter plane in history. This aircraft underwent a grueling 6-month assessment at the laboratory, where it was exposed to a variety of extreme weather conditions, including wind, solar radiation, fog, humidity, rain, ice, and snow. The goal was to certify the F-35's ability to operate in any environment, anywhere in the world. Even with all this preparation, however, ice formation on military aircraft in cold weather conditions remains a persistent challenge. To combat this, the Air Force and Navy employ a de-icing process similar to that used at commercial airports, but with a heightened sense of urgency. In military operations, there's no time to waste. Aircraft must be ready to take off and complete their missions no matter what. This relentless focus on readiness is what ensures that military forces can operate effectively in even the most extreme environments, including those marked by freezing cold. And when an airplane crosses paths with a flock of geese, the result is more than just a tragic fate for the birds. It's a serious threat to everyone on board. Even small birds can wreak havoc, causing an engine to stall or even explode. While bird strikes are mostly harmless to the plane itself, they're often deadly for the birds and incredibly costly for airlines. In fact, bird strikes cost the aviation industry around $1.2 billion in repairs each year. To tackle this, engine manufacturers conduct rigorous tests to ensure engines keep running even after a bird strike. How do they do it? With something called a chicken gun. This device, a large diameter compressed air cannon, was invented in the 1950s by de Havilland in the UK. It fires freshly killed chickens into test engines and cockpit windows at high speeds, simulating real-life bird strikes. These tests are critical for ensuring that the engines keep working and that the cockpit windshields can withstand such impacts without shattering or altering the plane's flight. Thanks for watching. If you enjoyed this video, make sure to hit that subscribe button so you don't miss any of our future content. See you next time.